Welcome back to the lecture series on computer-aided detailing of structures. That is subject code 17CVL77. That is CAD lab. Already we have completed about 7 to 8 labs. In still, I think they have completed, madam. But again, coming over to the RCC lab, I think we are almost we have covered 90%. Only 2-3 drawings may be left over here. So today we are going to make a drawing of water tanks. So water tanks, what the question will be given and what are the steps to be followed to draw that. So exactly what is given here. So we can see here the question, the drawing they have given. Design a circular water tanks. The question will be given in this fashion. Drawing a circular water tank of capacity 4 lakh liters, which is resting on a good yield, unyielding ground. The depth of tank is found to be 3.5 meters. A freeboard of 200 mm may be provided. The wall and the base are cast integrally, means they are homogenic. Then design the tank using M20 and MFE415 steel. So usually the question will be given in this pattern. You need to design and draw the things. So here are some design steps we can see here. We all learned in the class. Note on the given details first. So first they are given is a capacity of tank, that is 4 lakh liters. It is in liters, 4 lakh. Convert it into the volume, that is a meter cubic. So 4,000 divided by 4 lakh divided by 1,000, we get 400 cubic meter as the volume, that is capacity of a tank to be done. Next, they have given the height of a tank, that is total height of tank including freeboard. So total height of tank they have given is 3.5 meters. In this, they have given a 200 mm as the freeboard. So the capacity of tank inside is 3.3 meter height of water can be stored inside the tank. So volume is 4,400 meter cube, and the height of water to be stored inside the tank is 3.3 meters. So definitely the area of tank, that is in found to be 400 divided by the height 3.3. We get the area of tank as 121.2 meters square. So 121.2 meters square. Since it's a circular tank, we know the area of circular tank, that is pi by 4 d square equals to 121.2. So substituting, knowing the value of d here, so d is equal to under root of 4 by pi into the area that is required, that is 121.2. So substituting a value of 4 into 121.2 divided by pi under root, we get the diameter of tank required as 12.42 meters, which we are taking round off as 13, or even you can take 12.5 meter as the diameter of tank, and we can draw it. So once the tank is known, the size of tank is fixed here. We have calculated the size of tank. Height we was knowing 3.3, and the diameter we got is required is 12.4, and we are getting round about 13 meter we are providing. Then what could be the thickness of wall? So the thickness of wall, the assumption, there is a formula for that, that is 30 h plus 50. 50 is nothing but a coefficient we have given. So h is nothing but a height here. Again, height equals to what? 3.3 meter. Water storage is gone. So 30 into 3.33 plus 50, we get around about the thickness of required for wall is 149 mm. So we, instead of giving 150, we are giving on higher side 160 mm as the thickness of wall we are provided. And by knowing the thickness of wall, that is 160 mm, and the diameter of tank as 13 meters, make sure that there will be a single layer of reinforcement in 160 mm thickness of wall. Previously in the design components, we see that whenever the thickness of wall exceeds 200 and above, we can provide the 2 layer of reinforcement inside that. But since it's less than 200, we are providing only 1 layer of reinforcement, where we get vertical reinforcement as well as circular reinforcement. Circular reinforcement designed as a hoop for hoop tension. Since it's a circular wall, circular tank, force will be maximum in radial directions, that is circular. Hence, for hoop tension, the main reinforcement will be designed and provided in the form of circular here. And while the distribution bars, which is having less movement, will be designed in the vertical directions, and the vertical reinforcement provided are for movement, and they are provided for it as a distribution bar. So let us know this, that circular bars, the radial force will be more, and the main bars will be in the circular direction. So design of vertical wall here. To calculate the maximum hoop tension at the bottom of tank, since it is a fixed one, rigid, the base is rigid, the maximum force will be at the bottom of tank. So we know that the for calculation, the formula for hoop tension is density T is equal to rho H D by 2. Rho is nothing but the density of water. H is the height of water stored inside the tank, and D is the diameter of tank, what we have got. So substituting this value, that is density of water is 10 here, height of water is 3.3 meters, then the diameter is 13, that is divided by 2, that is radius we are going to calculate here. So rho HR is equal to the tension in the bottom of the tank, that we get is 214.5 kilonewtons. So once we got that hoop tension in the walls, what could be the reinforcement provided for that area? That is T divided by sigma ST. Sigma ST is nothing but a 150 here. So 2 is 214.5 kilonewton, that is 10 raised to 3, that is converted into newtons, divided by sigma ST, that is 150 Newton per mm square. So Newton get cancelled, left with mm square. So the area of steel required for this vertical wall maximum at hoop tension at the bottom of slab will be 1430 mm square. Let us check what could be the minimum steel if it is required. It is whether greater than the required or not. So usually in water retaining structures, the minimum steel provided will be 0.24% of the area of concrete. Area of concrete means the thickness of wall, that is capital D into the 1 meter width. So here the 0.24 into 100 into 1000 into 160 divided by 100, that will give the area of steel here. So area of steel for minimum will be 384 mm square, that is 0.24 divided by 100 into 1000 into 160. 1000 is a per meter and 160 is the thickness of tank, that we get is 384. And this 384 is very, very less compared to the maximum reinforcement part we got is 1430. So now let us assume the 16 mm dia bar we are going to provide in the as a hoop tension bars. So the number of bars or spacing of bars required for 16 mm dia will be the total area divided by the area of single bar into 1 meter width. That is 143 is the total area of bar required, area of steel required, into 1000, that is per meter, divided by 201, that the area of a single bar. So the spacing what we required for 16 mm dia bar is 140.6 mm. So we are going to provide 16 mm dia of 140 mm center to center, or we can provide less than 140. Here we are providing 1.6. But make sure that since it is a you can see the diagram, the height of tank, this thickness is 160. So let us take it as a 20 scale. So 160 here. So height is 3500 divided by 20. So this could be the height of tank here. We can see it will be like this. This will be 13. We can take it like this. But here we can see the total height is 3.3. The pressure acting over this will be in this fashion. The water pressure will be in this fashion. So that is maximum at the bottom here, like this. We have maximum bottom at the like this. So as the height of tank increases, the pressure goes on reducing. So maximum pressure will be at the bottom of tank. Since it is a rigid base, both walls and slab are homogeneous, we get the maximum reinforcement only at the bottom. So here we are providing 160 means the tank will be in this fashion. So here we are providing the main bars in this fashion here like this. Means this is a distribution bar we are providing. Thickness of slab, let us take it as somewhere about 300, no problem. We are assuming it. Later on we'll see how exactly it happens. So this is a bar here. So the reinforcement of this bar will be given like this. So you can see these are the bars provided at the distribution bars at the bottom slab, which are not yet designed, but I will show how it will provide. So our main bar will be like this. It will come and join like this. It will rest over this like this. So this is a vertical bar, which is a distribution bar we call. The main bars will be in a circular one, that is do not we can provide. So this is our main bar, which will be provided in this fashion. This spacing we are providing 140. So let us take it to spacing of 140 only. Copy this, let us provide it 140 divided by 20. So 140 means 280 divided by 20. So this is what we are spacing bars. And so we can provide the reinforcement in this fashion. So this is how we are providing. Let us take it for 1 meter height only. From here about 1 meter height we are doing that. 1 meter divided by 20. So up to this, you can say we can calculate like this from here to here it is. So up to this the pressure we are providing 16 at 140. Above this, what happens? As the pressure reduces, we doesn't require to provide the same spacing, because simply if we provide the same spacing of 160, there is no use. We are providing higher reinforcement still, which is not required at this level. At this level, the pressure is less. Again, after 1 meter of this, if you take this from here 1 meter again, yes, after this again there will be pressure reduced, so we can reduce the spacing from this to this. Here you are providing 16 at 120 like this. You can see here we are providing this bar like this. See how we can change this one here. So we can take here this one. So when we write this, this is a lead. How I wrote this after writing this. Take a remark of LE, leader. LE means leader, that is dimensions we can see here. Dimensions, if you get a leader here, somewhere here I got leader. Select this, select it on this row, drag it, we get a leaders here. Now I want to circular one here, so select this, then draw control one. After selecting this, draw control one. We get this chart, that is properties. Once we select this, we can see here lines and arrows, where we get arrow says here. So click on this, we get a small table. Open this, we can see number of tabs here. That is whether it is in closed section, whether open, rectangular, dotted, crossbar, whichever like we can take like this. And here I am selecting as a dot blank. So when you select this dot blank, I will get in this fashion. So we can write directly this, and the text for this I can copy here from the table itself, telling that what should be written here. So somewhere I am writing here. So we know that it is a tor bar here. So tor 16 mm at 140 mm center to center. So this is a reinforcement, hoop reinforcement, main reinforcement I am providing here. You can see it, you can write it here. Again, after this, knowing the pressure, we can check here. So how we are doing? 140 for main reinforcement. Before going this, they are checking for tensile truss. This should be less than 1.2. So 1.2 is a permissible stress. So how we find this stress here? That is stress in concrete, that is T by 100,000 T plus M minus 1 into sigma is area of scale. T tension we got 204. 100 T is the thickness of all. M is modular ratio. Modular ratio we are getting by formula 280 by 3 into sigma CBC. Sigma CBC is nothing but it is a bending stress in concrete due to M20 grade concrete. For that we can see here it is given in table IS 3370 part 2. If you see the tables are given, that is 7 for M20 grade concrete for bending stress. So substituting that value, we get 280 into 3 into 7, we get 13.3 is a modular ratio. And the area of steel already we know it is 201 into 1025 spacing 140, we get 1436. Substituting this, we are getting this 1.2, and the permission stress is nothing but is almost 1.2 only. So both are near same, though it is safe in a tensile stress. So curtailment of bar hoop station, as I told, as the height increases for 3.3 meter height, the spacing required is 116 by 140. When the height of water will be 2.3 meter, what will be the pressure? Substituting value of 10 into H is equal to 2.3, D is equal to D by 2 is nothing but 12.5. That is 13 divided by 6.5. We get the pressure tensile as 149.5. For this area of steel required is 996. Suppose if I are using 16 mm diapers, the spacing required will be 200. So as the height reduces, the tension increases and the area of steel also increases and the spacing also gets doubled here. So usually we should not exceed the spacing of 384. So here we are getting the 200 spacing. Let the third one be 300 and the last one be the 350. We should provide because it should not exceed 384. So this is how we are providing, and for height, for every 1 meter height, there is a change in spacing. So we can see here, after 1 meter height, this spacing can be changed to. So here it is up to, I am writing here. So this is also 140 divided by 20. So after this, the spacing will be almost 200. So this I can take like this. I can take it as 200 divided by 20. And after that 400 divided by 20. So the spacing is almost getting doubled here. So we can see last one, we can take this as like this as. So up to here the spacing is changed here. We can see I can copy this and I can write the same thing right here. So I'm writing here. After 1 meter height, I can write this as 16 mm by 8, 200 mm spacing. This is how we should show. Again, after this, after 1 meter, it becomes 300. So from here it will be 300, 600, 900. Look at here how we get the spacing. So we can say providing 3 here, so 300 divided by 20. And the last part we are providing at top. So after this, we can provide only one spacing. After this, I can take this as, and I can write this like this, 600 at 300 mm spacing. So we can see guys how the reinforcement is changing here. From here the spacing will be 140, from 1 meter height it will be 200, after 2 meter height it will be 300. So you should show that reinforcement like this only. Once we can coming over to the hoop tensions we have got, then we are going to design the vertical bars. Vertical reinforcement means they are usually done for temperature and shrinkage distribution bars. So we can see the minimum bar provided for the shrinkage and temperature reinforcement will be 0.24% of the gross area. So gross area means the thickness of tank is 160 into 1000 into 0.24 divided by 100. The area of steel required for the vertical reinforcement will be 384 mm square. So for this, let us use the 10 mm bars or 8 mm bars, whichever way we convenient. So here I am using 10 mm dia bars. So if you use 10 mm diameter of bar, spacing of bar required will be area of single bar into 1000 divided by the whole area, that is 204 mm required is steel when we provide 10 mm dia bar. So let us provide 10 mm dia bars of 200 mm center to center as a vertical bars distribution shown in the figure. So here we can see this will be shown like this. The leader I am taking, and reinforcement this number I am showing like this. It will be shown in this fashion. So this is 10 mm at 200 mm center to center. Okay, this is how we are showing the reinforcement, and I am going to note 1:20 here. So let us take this. It is no 1:20 here. So 1:20 is given here. Let us take 1:20. So 1:20, if I take, I can get the dimensions like this. This is 1 meter. Yes, this is second 1 meters. So we can show it like this. But in your regular practice, I say one thing I told to my every students, that whenever you write the dimensions, see that nothing gets overlapped here. Overlapping should not happen anywhere in the diagram. So here we are getting overlap. So consider it like this. We can move it like this up to here. So we can write this dimensions outside here. Like this, we can take it outside. So we can show it like this outside. 1 meter here. That spacing will be 140. Further 1 meter again from here, it will be 1 meter. Again 1 meter, it will be 100 by 200, 16 into 200. After this, there will be 3 parts. This is how we are going to show this main bars in the vertical bars. Vertical bars as well as reservoir bars are shown. Now coming to the bottom slab, as I told of, it is a firm ground, unyielding. So the movement carry capacity of this floor is more here. So here we can provide the minimum steel by taking the thickness of slab as 300 or 200 mm. So here they are assuming the thickness of slab as 150 mm. So it will be very less 150. Let us go with the slab thickness of 250 mm, which is resting on a ground with providing minimum steel of 0.3%. So 0.3% of reinforcement means what will be the reinforcement here? That's equals to, right, here, 0.3 times 250 times 1000 divided by 100. So the reinforcement will be how much? Let us calculate it. You can check here. 0.3 into 250 into 750 mm square. Providing the 2 layers or 1 layer. Let us check it whether we are providing 2 layers or 1 layer. So here we can see they have taken the thickness of slab as 200 here. Let us take 200 as a thickness of slab instead of 300. Let us take it as 200. So take 200, what could be the value? 200 into 10 into 0.3. 600 will be the area. So So total area of steel cord is 600. We can see it. So here we have written 600. So what could be the spacing if you use the 8 mm dia bars? So 8 mm dia means area of bar will be area of bar for 8 mm dia bar. How much will be area? 8 into 8. 8 into 8 into 3.142 divided by 4. That is 50.275. Divided by 300. What could be the area I'm getting here? Here is into 1000 divided by 300. So 160 spacing, 167. So we can provide a spacing of 1 center to center. Here the taken thickness very less. If I take thickness as 200 mm, so area of the record is 600, but we are providing 8 mm dia bars. 600 means we are providing it in 2 layers. So if you provide in 2 layers, what could be the reinforcement? 600 divided by 2. So that will be 300 mm square per face. So we can see here, we can provide reinforcement in 2 layers here. Plus I can say like this, otherwise I can provide it a reinforcement like this. Like this. See what are the options we can use to draw this. I take it like this. Here, the reinforcement are provided in this fashion. So this I can write leader, I can write it like this. Quick leader, I can take it like this. I can join this. Quick leader, I can take like this. I can join this. Quick leader, I can take like this. I can join it like this. Like this I can show. So control 1. So I can take this and this. I can take this arrow. We take this. So dot blank. I will be in blank size. So I can write reinforcement. So I can take this and I can write like this. We are providing 8 mm dia bars at 165 centimeter in all 4 ways. This is how the dimensions can be shown, dear friends. You can take this as 300 given. So I can reduce this stretch here. So how we can reduce this, I will show you without making any modification in a drawing. I will reduce this thickness here. Take a stretch command from modify. Here there is a stretch command. Connect this like this. So it is 300. Strike it like this. F8. That is 100 divided by 20. We get 200 directly. This is how it will be corrected. This is what we should learn in AutoCAD. Why I am telling to practice this means is there are some commands which you need to load like this. So it was 300. Without making any modification, I have directly made it to 200. This is how we should learn. And the thickness of wall we got is 160 like this. So this is what the reinforcement I showed. For this, this is a section I have shown. This I can take it as a the section I have shown. If you want to show the plan can be shown for the reinforcement, but think what happened here. The diameter is long here, 13, and the thickness of wall is only 160. So the reinforcement knot will be shown properly here. See here, we can show the like this. I can take a circle here. So circle I have taken the arcing radius here. The radius is, I think it is 6,500 divided by 100. If I take also what happens, this is a circular, and for this offset I will give as 160 the thickness of wall divided by 100. So this is our thickness of wall here. See here, in this I should provide the reinforcement. Again, I can provide like this. So offset, providing 30 as cover divided by 100. 30 cover I have given. So reinforcement will be provided like this. See here. Otherwise, offset 160 is 80 divided by 100. From this dotted I can this bonus to nuts. So we can provide reinforcement like this. If you feel this is a bigger diameter, you can see we can provide like this. These are the main bars. This is how it looks, but when we zoom it, we can see it. Otherwise, we can't see it. Only the diameter will be shown like this. Remaining part will be very less, which is negligible. We can't see it. So we can zoom it or we can reduce it and we can show the circular one in the diagram. This is how what we have learned in the today's class, how the water tank should be designed and how it could be detailed. So this needs more practice, my dear students. So if possible, if not coming over to college, there only in your home itself in AutoCAD you can learn this, know the commands very well. Try to solve by yourself. Don't copy the drawings. It's a good opportunity that if you practice at home itself, you can learn much more commands. Try it initially. You don't know the commands, so it will take much time to draw. But in examination, I told it's an offline exam, and the examination will be done for 3 hours, where you need to draw 2 drawings. One is RCC and one is steel. So you need to complete each drawing by 1 hour 50 minutes. 1 hour 30 minutes. Even 1 hour 13 minutes will be not sufficient. You may get 1 hour 20 minutes. So you need to submit it by 2 hours, 2.5 hours. So per drawing, you will get 1 hour 15 minutes to 20 minutes to complete it. So practice the things very well so that it will be easy for you to draw in the exams. If you practice by yourself, you can fastly draw it in your exams. Otherwise, it will be difficult for you to complete at least one drawings. Because if you without practice, you can't complete a drawing by an hour or 1.5 hours. If you practice only, then only you can complete the drawings by 1 hour, 1.5 hours. Because we need detailing also for that. Not only drawing, a detailing should be done. Along with that, you need to write the reinforcements also, I am telling. Not only writing the reinforcement, the dimension should be written for the scale. So you need to learn not only to make a draw, you need to draw for the scale, then write the dimensions, then I doesn't say that setting of paper will be done afterwards you're coming over to college. At least you draw the drawing for 1:1 scale in your home itself. Whatever dimensions is given for same dimensions, draw the diagrams and keep it in AutoCAD. When you come over to college, I will tell you how to scale it and fix it in a paper. That will be taught in one AutoCAD drawing class only. If you come offline, it will be taught in offline. If not, I will teach in online in the next class. So that setting of paper is very important. That the scaling of drawing. First, you will draw the drawing for 1:1 scale. Once you complete it, we will reduce it to the required scale and you will fit it in a paper and we will take a print. Why it is so important is, once if you take out the print in A4 or A3 side, if some dimensions are missing, if by chance I have not written 200 and I have taken a print, there is no thickness of slab is given. Instead of asking it, if you write the scale here, somewhere I will write the scale here, say it is 1:20, I will write a scale here. In this, I can write the scale like this. Suppose instead of writing here, I will it is shown like this. I will show it. So scale I have written 1:20. It will be written like this. Scale is 1:20. So that if I written like this 1:20 scale here, using your small scale, what is having, we can measure this when you take out the prints. So when you take out the print should be for the scale itself. Then only we will get the correct dimensions. That's what you need to. AutoCAD submission is not such an easy thing. You need to draw, not only drawing, making the drawings as per the dimensions and fitting it into the required scale in the required sheet, whether it is A3 sheet or A4 sheet or A2 sheets, wherever you required, that should be fit for the scale itself. When you take out the print, if you measure with whatever the scale is written on the paper, then it will be fine. So this should be learned in the offline class. It will be taught in the next coming class and also in online, if possible. Draw by yourself for 1:1 scale, so that next class I will tell you how to scale it and fit it in a paper. Is anybody having any doubts here? Dear students, anybody having any doubts? If you are having doubts, you are free to ask me. Yes, anybody? Hmm? Jay Shri.
Yes, sir.
Yes, no reply. So no doubts. Shall we conclude the class now? Yes, students, we are concluding the class. So because 11 o'clock I am having an offline class for your 7 sir. So let me close it and get ready for your offline class. Okay. Thank you guys. Thank you for patiently listening the class.